Hello, my name is Phillip Campbell, and I'm a member of the Mindel Legacy Teachable OS project, as well as a second-year PhD student here at Georgia Tech. I'm co-advised by Dr. Eric Vogel in the Department of Material Science and Engineering, and Dr. Judd Reedy in the Georgia Tech Research Institute. My research focuses on the use of novel materials to make electronics smaller, faster, more efficient, more widely available. Our specific approach uses a class of materials known as two-dimensional materials, composed of layers 1 to a few atoms thick, to achieve this goal. Two-dimensional materials have properties that span from insulating, which you get with something like hexagonal boron nitride, to more conductive, which you get with graphene or molybdenum disulfide. Because of this, there's an interesting range of properties that these materials have that can be used to make entire devices out of just stacks of two-dimensional materials. Two-dimensional materials are also interesting for a number of reasons. First, their behavior depends a lot on the environment that they're put in. For example, if you change the substrate that graphene is placed on, you can change the mobility by an order of magnitude or so. Second, because 2D materials only have bonding in plane rather than out of plane like you get in 3D materials, it's possible to form a perfect interface between materials, which is essential for ideal device performance. Third, these materials can be transferred from substrate to substrate, so that you can take them from a gross substrate, which is typically, in our case, a silicon wafer, and move them to a polymer. This becomes interesting when you think of flexible devices and our desire to create all sorts of devices that you can wear, or that you can place on curved surfaces. So two-dimensional materials are finding a lot of interest there. When we're characterizing these devices, the most basic structure we use is a transistor. It's a kind of electronic switch. A transistor is composed of 3 terminals: the gate, the source, and the drain. When the transistor is on, electrons flow from the source to the drain, and the actual flow of electrons is enabled or disabled by the gate. For digital logic applications, all of the operations are simplified down into being in an on or an off state, a binary 1 for on or 0 for off. The most common type of transistor used in devices today is called the MOSFET, the metal oxide semiconductor field effect transistor. Essentially what this means is that the gate is formed of a metal oxide semiconductor stack, basically a capacitor, which when you apply voltage to it affects the conductivity of the semiconductor portion, allowing electrons to flow between a source and a drain. There are 2 types of MOSFETs that we use. First, the NMOS, and second, the PMOS. The operation of the device is almost identical, with the exception that they form a complementary set. That means that when you apply a 1 or an on to the gate of an NMOS, the NMOS turns on. But when you apply that 1 to the gate of a PMOS, the PMOS turns off. Using just these 2 types of transistors, all of the logic circuits that run all of your electronics can be made. To help you better understand how electronics work, my Teachable Moments project is developing an Android application that lets you actually design logic circuits and build them and simulate their operation. By playing the app, you'll be able to create devices as simple as an inverter, just a 2-transistor circuit, and ranging up to something like a binary adder, which takes several logic gates to work. If you don't know what any of those words are, I'd encourage you to play the app to find out.